All right, so we go from talking about the different spectral qualities of light, or the different wavelengths of light across the spectrum, to how light quality varies throughout the day, and so that we can ask the question, when do plants absorb the most light? So the most logical answer to this question would be certainly during the day, perhaps at midday. But what is it about that light that that the quality of that light that is ideal for plants to absorb? Okay, so light can be characterized in a couple of ways. One way that we characterize light is by intensity, which is also referred to as irradiance, as well as photon fluence, which is a term that I don't use as often, but that's another term to refer to with this, how we can characterize light. And it's measured as basically the density of photons. So photon flux density, or micromoles per meter square per second. Okay, so at midday, when we would suggest that plants are most photosynthetically active, then the photon flux density, which we also can call PAR, or photosynthetically active radiation, photosynthetically active radiation, equals about 2,000, this is like maximum light intensity, 2,000 micromoles of photons per meter squared per second. In contrast, at dusk or at twilight, the photosynthetically active radiation equals about, we'll put it way over here next to this number, 10 micromoles of photons per meter square per second. So it's quite a drop in the intensity of light at dusk. All right. Also at midday, we could also characterize light by spectral quality, which is what we've been doing when we've talked about up here wavelengths of light. So the spectral quality varies throughout the day in the natural environment, such that daytime skylight is enriched in blue light. All right, and so that's in the region of 380 or 400 or 420 nanomoles or nanometers of wavelength. So this refers to essentially wavelengths. And then at dusk, there is, or twilight rather, or either way, because of the angle of the sun, this S-U-N, because of the sun's angle, and there is a greater scattering of blue light rays, which then leaves an enrichment of skylight in the red and orange light. And of course, there are pigments that can absorb red and orange light. Whoops! But because this at dusk is at such a low photon fluence, then we would, then the plant is not able to absorb as much light energy, even though it's at a spectral quality that it might be able to absorb. So there's less efficient photosynthesis at dusk. All right, so the pigments that we've been talking about, as we said earlier, vary in the types of wavelengths, the specific wavelengths that they can absorb. And so what are some characteristics, and we'll write this question down here. What are characteristics of different pigments, different photosynthetic pigments, or plant pigments that are involved in photosynthesis? All right. So the diagram that we see here on the left shows us chlorophyll. And there are different kinds of chlorophyll molecules in photosynthetic organisms. Most common in plants are chlorophyll A and B. And so chlorophyll in general is characterized by this porphyrin ring that is made up of nitrogen units here with magnesium at the center. So magnesium is critical, as well as nitrogen, for the production of chlorophyll. And then we have all these various hydrocarbon side chains that make up the porphyrin ring here. And then the hydrocarbon tails that actually attach or embed the chlorophyll molecule in the thylakoid membrane. So the hydrophobic tail here, or hydrocarbon tail, anchors the pigment in the membranes. But absorption of light occurs in the porphyrin ring. So chlorophyll A and B only differ by this one functional unit here, a methane versus molecule here with the oxygen attached. And that plus in combination with the placement of the chlorophyll molecule in the membrane does give chlorophyll A a different light absorption spectrum than chlorophyll B. All right, so chlorophyll in general are what we refer to as our green pigments because they reflect green light. And as we said earlier, that they absorb blue and red light. Now, specifically, as we recorded earlier, chlorophyll A absorbs light from 400 to 450 nanometers of light, plus 650 to 700. Whereas chlorophyll B, with a slightly different absorption spectrum, absorbs from 450 to 500 nanometers, plus about 590 to 650 nanometers of light. There we go. So the point of writing these ranges down is to show again how the pigments specialize in a particular range of light to absorb. All right, now chlorophyll B is considered an accessory pigment, whereas chlorophyll A is more of a primary pigment for light absorption. Chlorophyll B is an accessory pigment. We also have carotenoids that are considered accessory pigments. And carotenoids, just to write down some characteristics, these are the orange and yellow pigments. So you can think of your orange and yellow vegetables, carrots, squash. So these are the pigments that appear orange and yellow. They show up when chlorophyll A starts to break down in the fall, when leaves change color. And they absorb, remember, they absorb blue and green light, or in the blue-green region of the spectrum, not full-on green, but anywhere from 400 to 530 nanometers of light, wavelength of light. Now carotenoids also, we can see an example of a carotenoid down below here. Beta carotene has an important photoprotective function in that it absorbs excess incoming light energy and prevents the generation of free radicals, or it prevents oxidative damage. Here we go, prevents oxidative damage by absorbing excess light radiation. Or light energy. Okay, so beta carotene is shown in the diagram below here, the molecular structure, which we can see as one long hydrocarbon chain. So it's a hydrophobic molecule and is embedded in the light harvesting complex. Another type of accessory pigment or carotenoid would be the xanthophylls, and they appear as yellow pigments, and again are accessory pigments that help absorb light in the light harvesting complexes of the photosystems. So these are basic characteristics that we wanted to sort of jot down to take note of with these pigments, which help us understand why they appear certain colors and what colors light in the light spectrum they absorb. Which brings us to kind of a segue here into Chapter 7, where we're going to look at the actual processes involved in photosynthesis. So when you start the next video clip, then we'll kind of talk about the general reaction of photosynthesis. We'll write out the reaction and the reactants and the products, and look at where those reactants are coming from and what the products are used for.